Hello everybody. This is the second video for chapter 5 of the statistical learning class. So in the chapter 5 we are introducing classification methods. So at the end of the last lecture, we've discussed the k-nearest neighbors method for classification, which is a non-parametric method. Okay, so there's no parametric assumption about the linear boundaries or how the data was simulated. To make a classification, we basically look at surrounding neighbors and pick the class which is the most likely. Okay, so the k nearest neighbors is a very simple method, which is non-parametric. But now in this video, we will start introducing parametric methods for classification. So the first approach we're going to discuss is called the linear discriminant method, and the name of that method was chosen since the classification boundaries, so the boundaries between regions of the predictor space, which classify as the various respective classes, are portions of hyperplane. Okay, so we're going to see that the classification boundaries or decision boundaries are driven by hyperplanes, so this is why we call that linear discriminant. So in a linear discriminant approach, we're going to assume that the model or the data points were generated from a particular distribution. So first we have to assume the unconditional probability for all the various classes. So we define pi j being the unconditional probability some point is drawn from class J. And then also the linear discriminant approach. So I might say LDA. So LDA stands for linear discriminant analysis. So the LDA approach presumes that the conditional distribution of the predictors given you're in a class G, is multivariate normal with a mean vector mu j corresponding to the class, not mu g, corresponding to the class G, and covariance matrix sigma. Okay, so here, let's say in the previous example discussed, let's say we have a blue observation, then this LDA approach assumes that observations from the blue class are generated from a multivariate normal distribution. Now, one quick detail here, mu g, the mean vector for class G, it varies across the classes, so mu g differs when G differs, whereas the assumption is that the covariance matrix sigma is the same for all classes. Okay, so the only thing that varies when generating data points from the various classes is the mean vector. So this is why we say it's a parametric approach. It's because we assume that the predictors in a given class were generated from a given parametric distribution. So in practice, if we make this assumption, we nevertheless don't know the true parameters, the matrix sigma, mean vectors mu g for all classes G, and the unconditional probabilities pi g. So these must be estimated in practice if we want to apply the LDA approach. So to do that, a simple way for this is the method of moments. Okay, so one quick detail here, the matrix sigma, because it's common for all classes, this complicates a bit the things because we cannot, let's say, look only at blue observations to determine sigma or orange observations to determine sigma. We need to look at all of them. But the method of moments works well in that context. So let's denote stylized SG being the set of all observations for which the class is in G. Okay, so for example, F blue would be the set of all blue observations, and S orange would be the set of all orange observations in the previous example. So in that case, the unconditional probability of being in class G, we can estimate it as the total number of observations from class G in the data divided by the total number of observations. So simply the proportion of observations from class G in the data. And mu G, the mean vector for predictors in the class G, well, it can simply be approximated by the sample average of all predictors in the data set. And here, this average, it's a vectorial average. Okay, so for each predictor, you make the average. So for example, for the jth predictor, you make the sample average of all jth predictors from observation in class G, for instance. Okay, so these are pretty easy to compute. And now, so what we'd like to do is to pick sigma, and we'd like to take the sample or sample standard deviation or sample covariance matrix of all observations, but we cannot only use one class to do that. We have to use all points. So here is how to proceed in practice. So for each observation, we can define like the centered predictors as follows. So the centered predictors are the original predictors for that observation minus mu gi hat, where this is the estimated mean vector for the class of the ith observation. Okay, so for example, if observation I is blue, then x tilde I would be the predictors minus the mean vector for the blue class. Conversely, if the ith observation is orange, then x tilde I would be the predictors of that observation minus the mean vector of the orange class. So in that case, provided that this estimator mu hat is close to the true mean vector, then the x tilde I are approximately IID from a distribution 0, mean vector 0, and covariance matrix sigma. Okay, so it's approximately because this is not the true value. This is only an estimate of the mean vector. But if this was the exact mean vector, then the x tilde I would be exactly IID normal 0 sigma. So what we can do then is we can estimate sigma by taking the sample covariance matrix of all observations x tilde I. Okay, so now to estimate sigma, we take all observations, not only these from a single class, and these variables, we assume that they are they have a 0 expected value because we've centered them, and they all have the same covariance matrix. So because of that, we can make this approximation that the estimated element of the matrix JK is the sample covariance. Well, it's not the sample covariance. Well, it is because we've centered the observations. Okay, so it's the sample covariance of the observations x tilde. Okay, and then the matrix sigma hat is simply the matrix which contains all such elements here. Okay, so this gives a way to obtain estimates of the pi's, the probabilities of being in each class, unconditional probability of mu g, the mean vector for all class G, and sigma hat, the covariance matrix driving the generation of observations in all classes. Okay, so when we have that, so if we want to apply an LDA, then we can make these assumptions, originally estimate the parameters, and then what we want to do next is, let's say we have a complete new observation whose predictors are x0. We want to have a prediction for the class of that new observation, g0. So how can we do that? Well, we can apply, as we mentioned in the previous lecture, the Bayes rule to try to calculate the conditional distribution of the class of the new observation given its predictors. Okay, so let's say x0 are its predictors. We like to have the distribution. So here it wouldn't be a density, it would be a mass function because G is quantitative, so has a finite number of values with a positive mass. So here we want the conditional mass function of the class given the predictors. So if we apply the Bayes rule here, this entails that the distribution of G given X for a given class G given observations X0, we can this is equal to the joint distribution of X. Okay, so this guy, maybe I'll write it. This on the top, it's the joint distribution of X and G, which is equal to Fx given G times Fg. This is a comma. Okay, and this is like conditional. So we can see that to obtain the conditional distribution of G given X, we can have an expression which depends on the conditional distribution of X given G. And then this quantity here, we know it because this is the multivariate normal distribution we've considered. We've assumed earlier in LDA assumption. Okay, so here we have this divided by the marginal distribution of predictors. So here, to go from here to here, what happens is that the first expression, f of x given g, is phi g x0. So this is the normal distribution with mean vector mu g and covariance matrix sigma we've assumed earlier. And then the mass function of g of the class evaluated as small g, it's pi g, the probability, unconditional probability of being in class G, which is good. And then to go from here to here, we simply have to notice that the denominator does not depend on G. So when we try to maximize the left side with respect to G to find the most likely class, this is equivalent to maximizing this quantity because the denominator is constant for all G, so it has no impact to find the minimizing argument. Okay. So in the LDA approach, once again, we're going to use the Bayes classifier idea where we try to categorize, or we classify an observation as the most likely class given its predictors. Okay, so for the new observation, its estimated class will be the class which maximizes the conditional probability of being in that class given the predictors. And we saw in the previous slide that this guy is proportional to this guy. So the estimated probability of being generating predictors x0 if you're in class G times pi g. Okay, so here we saw that this is proportional to this, so this means that this is proportional to this. And here, when we maximize a quantity, we can also maximize the log of that quantity because the log is an increasing function. And the log of this times this is the sum of logs. Okay, so the log of a times b is the log of a plus the log of b. So to go from here to here, we have to notice that these terms here, the first three terms, is the log PDF of the multivariate normal distribution. And here, the last term here is the log of this quantity. And the log of the multivariate normal PDF, well, recall if we go back to the Gaussian PDF, when we take the log, it's basically the interior here, which is the Malana-Hobis distance between xi and mu, minus the log of this quantity. Okay, so here, if we go back here, we have minus the log of the denominator and plus the interior of the exponential, which is this. And here, how to go from here to here, we simply have to notice first that this quantity does not depend on g, so we can remove it because it's constant for all g's. And furthermore, well, that's it. Okay, so this is what we do to go from here to here. Okay, so let's memorize this. So here, what we do to go from here to here is the following. Let's go back. So here we're gonna simply expand this square, well, product of 3 terms. Okay, so this product, it can be decomposed into 4 terms. It's x0 times this times x0 plus minus mu times this times x0 plus x0 times this times minus mu plus minus mu times this times minus mu. Okay, so we can expand this product here and get the following quantity. So we still have the first quantity here, the log of pi hat, and here this is the term where we have x0 and x0. At the end is the term where we have mu and mu. And here, to get this middle term here, we simply have to notice that mu transpose sigma minus 1 x0 is equal to x0 transposed here mu t. And the reason for that is if this quantity here, it has a 1 by 1 dimension. So because it's 1 by 1, we can transpose it and it doesn't change anything. So if we transpose that, it becomes x0 transpose times this transpose, which is x0 transpose times this transpose times, oops, the transpose here shouldn't be there. Okay, please remove this one, but times mu. And also because the matrix sigma is symmetrical, then or asymmetric, then sigma inverse is also symmetric. So because of that, sigma inverse transpose is equal to sigma inverse. So this is why the transpose is not there. Okay, so this term contains 2 of the terms in the expansion of the previous square, or the previous product. Okay, and then to go from here to here, we notice that this term, which has x0 and x0, there's no g anywhere that appears there, so we can remove it when we do the maximization, and then we obtain the following quantity. Okay, so all these terms, this is 1 by 1, this is 1 by 1, and this is 1 by 1, so it's really, this entails maximizing a scalar. So what we can do here, we can take this expression and define Cj and Bj according to the following rule. Okay, so Cj, we can define it as this term plus this term. Okay, so this and the minus 1 mu transpose sigma inverse mu. This is Cj, and then this middle term here, we can use the first part here to define Bg. Sorry, I said J, but it's really G. Okay, Bg times x0. So here Cg and Bg, they're constants. Okay, so here Cg is a 1 by 1 constant, and Bg, it's a 1 by p vector. Okay, where p is the number of predictors. Okay, so in this case, Bg is 1 by p, x0 is p by 1. So, yeah, this is it. Okay, this entails maximizing some scalar. So, summarizing what we just said, finding the most likely class, G, for a new observation is equivalent to trying to find the class G, which maximizes this linear expression where Cg and Bg are not random variables. They're constant, like a constant scalar and a constant scalar vector. But what I mean by constant, I mean deterministic, but this changes across the G. So we can use this and define a new function, define the function fg of x being Cg plus Bg of x. So the idea here is we say that for a given set of predictors x, the observation is classified as class G if this G yields the maximum value for this expression. Okay, so the problem G hat is to maximize across G C G plus BGX, where X are the predictors associated with the observation. So for that reason, the decision frontiers or decision boundaries, which are the place where we're indifferent between classifying into two classes, are or more than two classes, are of the following form. So decision boundaries, which split the predictor space into classification regions for all the classes, are of the form as follows. So we say that X is in the decision boundary if there exist two classes G1 and G2, such that fg1 of x is equal to fg2 of x, which means that for that x, you're indifferent between classifying within class 1 and class 2. And furthermore, for any other class G3, different than G1 and G2, then the probability of being in class either G1 or G2 is strictly or is greater or equal to the function fg3. Okay, so for that reason, the decision boundaries here, well, characterized by this set of equation, would be the set of points for which you're indifferent between classifying as G1 or G2, and that the G1 and G2 variables are as likely, at least as likely as any other possible classes G3. Okay, so the first condition here, which means that you're indifferent between classifying between class G1 and G2, can be expressed as this. So fg1x is equal to fg2x. So recall that if we go back one slide, fg is cg plus bgx. So here so let's write that fg is equal to cg plus bgx. Okay, so for that reason, fg1 being equal to fg2, this entails having bg1 by this bg2x plus the difference between the cg's is equal to 0. Okay, so the set of all x's or all predictor values which solves this equation here defines a hyperplane in RP. Okay, so this, you've seen this in probably in linear algebra. These type of linear equations provide solutions which for x which are hyperplanes. Okay, so we see that the set of all x's which satisfy this are hyperplanes, and then the second condition entails that, which is that fg1 is greater or equal to fg3 for all other classes G3. This entails that only a portion of the hyperplane are within the decision boundaries. Okay, because between among this set, you only need to pick x's which satisfy this additional constraint. So some of the x's might be dropped from that set. So we see that the decision frontiers are hyperplane, only portions of hyperplanes. Okay, so this might seem abstract right now, but in a few minutes we'll see a figure which will make that much more concrete. Okay, so in a nutshell, within a linear discriminant analysis, the decision boundaries are portions of hyperplanes in RP. So this is why we call them linear discriminant, because hyperplanes are just linear functions. Okay, whoops. So before going back to the example, maybe I'll have a figure to illustrate that. Okay, so let's say we have three classes uh, three classes. So let's say this is the possible values of x1 and x2. Okay, so maybe we have three classes, red, blue, and yellow. So I'll take another color, maybe gray. So maybe this plane represents indifference between red and yellow. Maybe this plane represents indifference between red and blue. And maybe this plane represents indifference between yellow and blue. Okay, so here, all these three hyperplanes would be the one which satisfy these for the various possible values of G. But decision boundaries, probably that you'd have something like, okay, you classify as yellow here, you classify as red here, and then you classify as blue here in this region. Okay, so what we meant when we said that the decision boundaries are only portions of the hyperplane is because here we see that the decision boundaries or frontier are this, this, and this. Okay, so whoops, we see that here you don't use the full hyperplane to classify. You only use this portion of the hyperplane. Same thing here. You only use this portion of the hyperplane to classify. You don't use the full hyperplane, and same thing here. Okay, so this is why we observe within this simple example that in a linear discriminant analysis, the decision regions or the areas in which you classify in the various classes are decided through hyperplanes, but we don't need to consider the entire hyperplane to make the classification, only the segment. And so this segment is determined by the other condition here. Okay, so for example, in this place, clear you're indifferent between red and yellow, but it doesn't matter because anyways it's blue that is preferable. Okay, so you don't need this part of the hyperplane. Okay, so this illustrates that for LDA, the classification is done through hyperplanes, and the decision region is obtained through portions of hyperplanes. Okay, so now let's go back to our original example where we had orange dots and blue dots. So this is the same original data we had, and recall that the red line which we obtained earlier is the Bayes classifier. Okay, so the red line is the optimal classification we could obtain if we want to minimize the training error. Okay, so now let's say we apply the LDA approach, then on this same data, then the decision frontier we would obtain is the green line here. Okay, so on this side of the green line, the points are classified as blue. On this side of the green line, so everywhere here, points are classified as orange. So we see here that the linear discriminant does a reasonably good job, but again, having a linear hyperplane to separate, here it's not flexible enough to have the suitable representation of the true pattern to properly classify. Okay, so we see that linear discriminant analysis can be fine, but in cases where the suitable decision region is not characterized by a straight line like this, then this model will have bias. Okay, but as we mentioned earlier, bias can be acceptable if it reduces the variability of your prediction. Okay, so is it good in practice? Well, it depends on any problem. So you have to try it to determine if it's good. Now, one thing I want to discuss here is the nature of predictors. So in, let's say, the k-nearest neighbors, well, even this, but here we have, forget about my previous sentence, but here the assumption was that the predictors were generated from a multivariate normal distribution. So this method might not work very well if you have qualitative predictors. Okay, so clearly if you have predictors which are qualitative or are factors, then the assumptions made by the model clearly fail. Okay, so in practice, sometimes the assumptions fail, but you still have decent result. But this method here, it really shows it's not tailor-made to work with qualitative predictors. Okay, so we've seen the application of linear discriminant analysis, and we've seen that this provides, this drives the classification by a frontier which has the shape of a straight line. Now what we're going to do next is to present a second method which aims at generalizing the linear discriminant analysis, and this second method is called quadratic discriminant analysis. So the reason why quadratic, we can already have thoughts about what it's going to be. It's instead of having straight lines to as decision boundaries, the decision boundaries under this approach will be quadratic functions instead, which yields additional flexibility. Okay, so how do we come up with these quadratic boundaries? Well, we're going to see that these quadratic boundaries, they come from solving some quadratic equations that we are going to outline in the next slides. And because these are, as we said, these are quadratic, so these are more flexible than linear functions and can have less bias in problems where the true decision boundary is not linear. So how do we obtain these classifiers? Well, they basically are obtained pretty much in the same way that we did for linear discriminant analysis, but we will make one minor difference in the assumptions, and making this different assumption, we're going to see changes the final result. And what's that difference? Well, for linear discriminant analysis, recall that the variance sigma that, used to generate data according to assumptions was constant across the various classes. Conversely, for quadratic discriminant analysis, we're going to assume that this matrix sigma varies across the various classes. So instead of having a single sigma, you have one sigma g, where you have one such sigma g per class or per group. Okay, so the assumptions underlying quadratic discriminant analysis are analogous to these from the LDA. So we have here, we're still going to denote by pi g the unconditional probability that an observation is from class G. And then we're going to assume that given an observation is from class small g, the distribution of its predictors is still multivariate normal, but this time with a mean vector mu g, which depends on g, but a covariance matrix which also depends on g. So the various classes have various different covariance matrices to generate their observations. Okay, so the difference is here for QDA. QDA stands for quadratic discriminant analysis. So for QDA, it's both the mean vector and the covariance matrix in the distribution of the x's, which vary across classes. Okay, so once again, if you want to apply quadratic discriminant analysis, you have to estimate the parameters, the unconditional probabilities of being in each class, the mean vector for predictors in each class, and the covariance of predictors in each class. Now, there are more parameters because you have one sigma per class, but a bit ironically, this makes the estimation a bit more simple, uh, as we're going to see next. Okay, so because the covariance matrix is not common to all classes, it's easier to apply the conventional maximum likelihood estimation method. So how to do that? Well, again, we're going to proceed as we did. SG represents the sets of all observations whose response is class G. And then, exactly as we did before, pi G is the proportion of observations which are from class G. Mu hat G is the sample average, where the sample average is a vectorial average of predictors within the class G. But now, through maximum likelihood, the covariance matrix here for class G can be simply used as the sample covariance matrix for all observations in class G. And note here, if we truly use maximum likelihood, there wouldn't be any -1 here, but here we make -1 here, which is called the Bessel correction, to ensure that this estimate is an unbiased estimate of the true covariance matrix. Okay, so this Bessel correction, this is a topic discussed in like, let's say, Stat 101 class. Okay. So once again, in a linear discriminant approach, we had the following, which was that the conditional mass function of the class given the predictors was proportional to the Gaussian distribution in class G times pi G. Well, this result still holds for a quadratic discriminant analysis. Okay, so we won't rederive this. Please go back a few slides. You might pause the video here. Go back a few slides to see that you can apply exactly the same calculations for QDA than LDA, and this relationship still holds. And therefore, if you want to find if you have a completely new observation, you'd like to classify this observation, and the forecast or forecasted class for this new observation is the one which maximizes the conditional probability of being in that class given your predictors. And because of this relationship, we can substitute this by this in the maximization. So replace this by this, and we can also take the log, because the log is an increasing function. And exactly as we did, the log of this times this is the log of this plus the log of this. So this becomes the log of the Gaussian density plus the log of the probability. And here, to go from here to here, what happens, we have to notice that, okay, let's show that here. The log of square root 2 pi to the power p times the discriminant of sigma g is equal to some constant. I'll write it like this, plus 1/2 the log of, so this is a p here, the log of the determinant of sigma g. Okay, so this is why, to go from here to here, we simply can replace this guy by this guy, because there's a constant that should be here, but the constant can be removed because it doesn't depend on g. Okay, so the constant would be the log of square root of 2 pi to the power p. Okay, that's good. So then, to go to the next step, once again, the same thing applies that we did earlier. So we can expand this product. So we can take this expression, expand this product, and if we do that, then we have many terms. And then, again, the same type of calculations can be applied. I won't repeat that here. Feel free to pause the video and continue calculations until you arrive at the end, and eventually, if you define the following quantities: A tilde G is equal to minus 1 times the inverse covariance matrix, B tilde G is equal to this, C tilde G is equal to this. Then this expression, so the estimated class is to maximize across G. This expression becomes the estimated class is to find the class which maximizes this expression here, which can be expressed as this. Okay, so here you can do the math at your own pace, but eventually you should come up and show that the estimated class, based on what we saw, is to find the class G which maximizes this. And here we see that we have something different here, because this in the previous the previous QDA, we had a linear equation, so we didn't have any quadratic term here, and the expression for C was a bit different. So this is why I've put tildes here. It's because the CG here and the CG from the previous LDA are different. So here, this is why I've put tilde to show that they're different. But the idea here is in LDA, we didn't have any quadratic term here. So the G simply had to maximize a linear expression across G. But now that we have a quadratic, now that we have sigma that varies across G, there's a new term which is the quadratic term here. And we can see why this wasn't there before. It's because if sigma G was constant across G, then this A tilde G would have been constant, and therefore this term would not have depended on G, so you could have dropped it. But now, because sigma G depends on G, this new term is here. So we see that finding making the forecast for the class of the new observation entails maximizing across all classes this expression, where this is a quadratic expression with respect to the predictors x0. So we can do the same thing we did earlier, define the function f(g(x), which is this quadratic expression of x with constants c tilde g, b tilde g, and a tilde g being defined as in previous slide, where here this is 1 by 1, this is 1 by p, and here A tilde, it's the minus 1/2 the inverse covariance matrix, so this A tilde G is a p by p deterministic matrix. So as we discussed earlier, we define these, and the decision boundaries are the values for x for which there exists two classes G1 and G2, such that this function is the same for G1 and G2. So on that boundary, you would be indifferent between classifying as G1 or G2. And here, you might have this here, where for all other classes G3, then you would be at least as likely to be in class G1 and G3. Okay, so all x's which satisfy these constraints for some G1 and G2 are part of the decision boundaries in the quadratic discriminant analysis. Okay, so the first condition here, if we apply this becomes the following. So fg1 tilde is equal to fg2 tilde. Well, we can replace fg1 and fg2, so recall that fgx is cg plus bgx plus x transpose agx. So we can substitute the f's by this expression, and this, if we do that, we obtain the following expression. So here there shouldn't be i's here. This I shouldn't be there. This I shouldn't be there. But we obtain the following expression here. And so solving for the x's, which equate this expression to 0, is a quadratic equation. So the decision frontiers obtained by this method would be characterized by quadratic expressions or functions in the predictor space. And this is why we call the approach quadratic discriminant analysis, because the solution to these to identify the decision frontiers are quadratic functions within the predictor space. So here, when we say quadratic functions, these could have different shapes based on the values of a tilde, b tilde, c tilde. So there are different types of quadratic function: ellipses, hyperbolas, parabolas, etc. Okay, so there are various possible shapes for classification within a quadratic discriminant analysis. Okay, and similarly, as we discussed before, the second condition where G1 and G2 would be preferred to any other classes, G3, entails that only a portion of the quadratic regions would be within decision boundaries. Often it's not the entire quadratic curve. Okay, so we can go back once again to our previous examples where we had fictitious generated data. So here we have our blue dots, the orange dots, which are data points. Recall that the red curve is the base decision frontier, which would be the optimal decision frontier if we wanted to minimize the prediction error. So, and by prediction error, I mean the expected error rate out of sample. And then we applied the quadratic discriminant analysis, and we see that we've obtained a quadratic curve to classify. So on this side of the green curve, we would classify as blue. On that side of the green curve, we would classify as orange. Okay. But now there's one question that emerges here: is why aren't the red and green curves overlapping here? Because if we go back to the way this fictitious data was generated, the data was generated exactly according to assumptions of the quadratic discriminant analysis. Okay, so the assumptions made by QDA is that the predictors in each class are simulated from a multivariate normal distribution depending on the class. So this is the assumption made by the base classifier, made by the quadratic discriminant analysis, and this is exactly the way we generate data points. So if the assumptions from QDA is consistent with the way data points were generated, how come the QDA decision frontier doesn't match with the optimal frontier? And the reason is simple. It's because the base classifier knows the true value of the parameters. Okay, it assumes that we know exactly the true values of the Gaussian distribution, whereas the quadratic discriminant had to estimate the parameters, so it used parameter estimates instead of the true value. So this is why both methods yield different decision boundaries. But if the estimated parameters exactly matched the true parameters, then both decision frontiers from the base classifier and the quadratic discriminant analysis would exactly match, because the assumption of QDA exactly matches the way we've simulated the data. Okay, so now we have linear discriminant analysis and quadratic discriminant analysis. So which one is better in practice? You might think, well, quadratic discriminant analysis is more flexible, so it should be able to represent more varied patterns. and it might be better? Well, the answer is not that clear, and the reason is why quadratic discriminant analysis, because it's more flexible, it has more parameters to estimate, and thus more parameters entails more flexibility, and more flexibility increases the risk of overfitting. Okay, so you have more variability in your predictions when you use a more flexible model. And too much variability, we saw that although this increases performance in sample, this might decrease out of sample performance due to overfitting. So it's not clear in practice if linear discriminant analysis or quadratic discriminant analysis is better. You have to try it, and once you try it, then you see which one performs the best for your particular problem. Okay, so some problems where the true decision frontier is approximately linear might be better handled with linear discriminant analysis, or if the true decision frontier is far from linear, then maybe QDA might be better because LDA would be too biased. Okay, so the optimal of trade-off between bias and variance is not known in advance, so you have to try it in practice to see which one works best for your given problem. Okay, so you have to fit your models on training sets and then estimate their performance out of sample. So that can be done if you have a test set, or you could do, for example, a cross-validation to see how your method works or how well it performs. Okay, so these are two parametric approaches for classification, which relied on the assumption that predictors were generated from Gaussian distributions. So we'll stop here, but in the next lecture we'll see other classification methods which do not necessarily rely on this normality assumption for predictors, but nevertheless are parametric. So I'll stop there, but I'll see you next time for the next lecture.